So in this chapter, or section 5.7, we're going to talk about change of variables for for integration with two variables and three and so forth. I need a couple definitions to give you first before we can start in on that process. The first one is a one-to-one transformation. So if you recall from probably just algebra, a one-to-one transform or a one-to-one function is, you have, say, x values and say y values. So that means each individual x value can map to one y, and no two x values will map to the same y. So a one-to-one relationship could be something like this, where if the only x values we have are 0, 1, 2, 3, each of them map to an individual y value. No, we don't have two of them going to 3 or multiples going to a single number. That would be considered one-to-one. In the same vein here, a one-to-one transformation happens if we have no 2 points mapping to the same image point, where, this is your image over here. The second definition deals with something called a Jacobian. So really, this is going to just be dealing with partial derivatives. So the notation, first of all, again, we've got this notation here, this capital J, parentheses, ordinal pair of u, comma, v. And we've got this part here. Sometimes this is actually written like this, just, But we know that we're taking the determinant of it, so we just may have something like, J, U, V equaling that. So if your book has notation like that, that's where it's coming from. All right, so what we do here is we take partial derivatives, which you know how to do already. So we make a 2 by 2 determinant. We take the derivative of x with respect to u. That's our a our 1, 1 coordinate. Our 1, 2 coordinate was the derivative of y with respect to u. And then our 2, 1 would be the derivative of x with respect to v. And our 2, 2 would be the derivative of derivative of y with respect to v. And you take the determinant in the same manner that you would. You multiply the down diagonal together, those two together, and you subtract them from the up diagonal. And that's where we get our formula there. So I'm going to do one of these in practice here. So number 378 from your book in 5.7, excuse me, we're given the x is equal to u plus 2v and y equals negative u plus v. They just want the Jacobian. So we want the Jacobian of u, v, and we need to find the partial derivatives here. So our first value we need is dx du. So we look at the first one, x, taken to a derivative of 2 is just 1. Because the derivative of 2v, when we're taking it with respect to u, is going to be 0. So if you want, it's 1 plus 0 equals 1, and the 1 goes here. And then we have dy du. So we look at our y function on the right, and derivative with respect to u is going to be negative 1, because the derivative of negative u is negative 1. So that's negative 1, and the negative 1 goes here. Then we have, on the bottom left, we have dx dv. So we take the derivative with that with respect to v, that this time our u is a constant, so that's 0 plus 2, which is 2. So the 2 goes here, and finally, let's try green. We're going to take dy dv, and that is going to equal just 1. So 0 plus 1 is equal to 1, and we have a 1 there. So this all equals our diagonal down. So it's going to be 1 times 1. Let's try to keep these away from each other. And it's going to be minus the upward diagonal, which is going to be 2 times negative 1. And equals 1 minus a negative 2. So that equals 3. And that's how you take a Jacobian, at least for a 2 by 2.